All right, recording, back going. We're about halfway through class, and I want to tackle the most commonly asked questions that have been asked today. All right, so I'm going to hit these real fast. So one commonly asked question is number 61. We got these two gears in contact. It says compare the linear speed of the teeth to the angular speed of the gears. Okay, and I got this right here. So you guys can see this in motion. Okay, now do you guys see? Here, if I pop this apart, you can see underneath this one. You guys see some teeth on the right side, teeth on the left side, but they got different radial sizes of these gears. Okay, do you see at the point where the teeth come together? And guys, if you point a radar gun at this tooth right here and a radar gun at this tooth right here, do those radar guns read the same linear speed for the teeth? They do. Those speed match. Right? Right. But these two gears have different radial sizes, which kind of reminds me of this right here. It's like two turntables with different radial sizes. Okay? Guys, if the point where the teeth are meshing together have the same linear speed, but these two discs have different radial sizes, are they going to have different angular velocities? Yeah, right. In fact, I bet you guys can see which one's rotating faster. Oh, like if I rotate the one on the right side all the way around once, then how much does the one on the left side rotate around? Yeah, a lot more, right? In fact, if the radial size ratio is 2 to 1, I think it's pretty close to 2 to 1. Do you think that the one on the right rotates around once? The one on the left rotates around maybe twice, right? And then per unit time, like if that took like a second to go around, which one is spinning faster? The one on the left. Okay, so the guiding formula goes V equals omega R. That's what I just showed you from that poster with the purple banner, right? And on the other side, it's also equal to the other omega R. So maybe we call it omega A R A equals V, which is also equal to omega B R B. Okay? Right, so different radial sizes, different angular velocities. Okay, see that? Right, and the small one is going to spin faster. Okay? Right. But they have the same linear speed at the point of the teeth. Right. Next common question, videotape. When a videotape is rewound, why does it wind up fastest toward the end? And some students have been telling me, oh, they don't even know exactly what this looks like. Yeah, that's actually true because almost everything's digital now. But if you go back to like the 1990s, when I was a kid, you used to have like these video rental stores like Blockbuster, and you go with your friends and pick out a tape, right? These big old clunky tape. Or how about a cassette? You guys know those old cassette tapes? It's the same type principle. So it worked like this. There'd be like a spool here and a spool here. I'm going to show you guys the beginning and end, right? And maybe at the beginning of the tape, right? Beginning of the movie, beginning of the cassette tape, all the tape was around one side, and then it like loops around to the other side here, but maybe there's only a little bit, right? Then you play this, and over the course, the tape transfers from left to right, and by the time you get to the end, maybe it looks something more like this, right? And now we got all the tape on the other side, right? And have you guys ever heard a phrase called "be kind, rewind"? Yeah, all right, because back in the 90s, once you finish the tape, if you rewind it and before you give it back to the rental store, then the next customer doesn't have to rewind it. It's kind of a nice courtesy favor, right? Right. So here's what it looks like at the beginning. Here's what it looks like at the end, right? Now, if you hit rewind, you might be sitting there a few minutes for it to rewind. So you want it to rewind as fast as possible. And probably the easiest way to engineer the VHS player, is just to have this gear just turn at a constant angular velocity, right? Just, right. Ooh, this is sort of reminding me of like V equals omega R, okay, something like that. Okay. So see, I have a constant angular velocity, and at first it starts out this real small radius. So do you think when it starts rotating, starts rewinding, that this tape moves really slowly, right? Because this is a real small circumference, right, per rotation, right? Okay. But the more and more it rewinds, it looks more and more like this picture back on the left where how it started. Guys, and if this makes a full rotation, whoa, look at that big old circumference right there. So if this omega is constant, because it's just rotating at a constant rate, and this R is increasing, do you guys see that V, which is the linear speed of the tape rewinding, is also going to increase? You guys see that? Right. Right. Oh, what else has been asked? Let's look at the steering wheel number 74. Says it rotates so many degrees and the radius is so many centimeters. How far does a point on the edge move? Right. Well, that actually it's the same poster. It's a different equation though. You guys see this one at the top? X equals theta R. That's the guiding formula. One of the tricks is you do have to convert. Guys, this theta only works if it's in what unit? Not degrees, but radians. It has to be in radians. So I would kickstart this with a conversion. Let's do 74. I'll say theta equals. Now they did tell you theta, but it's in degrees, 128 degrees. Right. Do you guys remember railroad tracks? Do some unit conversion. Right. Guys, one trip around the circle is how many degrees? 360. And how many radians is that? 2 pi. Okay, so 360 degrees equivalent to 2 pi radians. I get some number of radians out of that. And now you can apply the distance moved is theta times r, because now you have the theta and radians, whatever that is, feeds right in there. Okay. Times so many centimeters radius gives you so many centimeters of moves. Okay, another question. Ooh, let's look at these propellers. 75 and 76 are connected. It says a propeller spins at so many revolutions per minute. You guys ever heard RPM, revolutions per minute? Okay, now that is an angular velocity. So I'm going to start out like that. I'll say angular velocity equals, right, some number of revolutions per minute. But you guys know in this class, if you want to apply formulas, like this set of formulas or any of these kinematic formulas right here, you can't use radians. Sorry, you cannot use revolutions per minute for omega. You have to use what? Radians per second? Radians per second? Okay. It's just a different way to quantify, kind of like inches versus meters. Something. All right. So I'm going to set up another set of railroad tracks right here. Here's stuff. Okay. How can I convert revolutions per minute to radians per second? Well, let's do one piece at a time. Guys, one revolution is how many radians again? 2 pi? Right? Does the number 2 pi go on top or on bottom? Okay. It has to go on top because it's attached to radians. And then per one revolution, like that fraction is equal to 1 because numerator and denominator are physically the same. Okay. You guys see I set it up in such a way that revolutions cancels. Okay. Now I got radians per minute. I want radians per second. You guys know there's 60 seconds in a minute. Does the number 60 go on top or on bottom? Yeah, on bottom. Because 1 minute is 60 seconds. Now the minutes goes what? You see now you're left with radians per second. So multiply across the top, divide by 60 down there. It gives you some number of radians per second. Okay? So then you're allowed to move forward to whatever they asked and start applying these formulas. Right? Like this. Because we got this in SI units. What's the angular velocity? Oh, actually, that was question A. We just walked through that. What is the angular displacement after so much time? Well, if it's a constant angular velocity, it's a simplified version of this first kinematic formula. Because it's not speeding up spinning, so this alpha is 0. Guys, isn't it just that right there? Is the answer to part B? Here's how far it rotates in radians. Here's how fast it's rotating, which we just found. And here's how much time which they gave you. Okay, you guys see that? Okay. All right. Well, it's like propeller slows from something to something in so much time. What's the angular acceleration? So this is number 76. And number 76. So similar consideration. I want to convert radians per minute to revolutions per minute into radians per second, which I just showed you guys how to do right here. So we just covered that. Okay. Right. Now, if it says it's slowing down, now it does have an angular acceleration. So there is some alpha that applies. So one of these formulas, you have to use the full formula. Okay. Guys, which one? They told you how fast it was rotating, how fast it ends up rotating because it slows down. And did they say how much time? Was that the question? No, sorry. They told you how much time, and they asked what's the angular acceleration. Which formula is that? First, second, or third? That's the second one right here. Because they told you how much time, right? And they told you the 2 angular velocity. Well, you have to convert to get radians per second, but there's the values are there, right? You have this, and they gave you the time, so you can solve for that alpha. You guys see that? Okay, so 76 right there. All right, and on the flip side, I've been getting questions about these two, so I'm going to hit these two and then leave you guys with that. Right. So number 90, topsoil. We got the stack of topsoil. Now they told you the weight of one bag. Ooh, that's nice because they couldn't give you mass. You have to solve for the weight. They went ahead and gave you the weight, but it's only for one bag. Because if there's 10 bags, you have to take the weight for one bag and multiply by 10. Right? That's one of the steps. Right? And the question is, what's the support force? Like, there's a couple of guys on either end, guy on the left, guy on the right. How much force does each person have to pull up with? Now, one of the simplifications, if you read it, is they said ignore the weight of the plywood itself because maybe it's so small in comparison to this stack of topsoil bags right here. Right? but I got a guy on the left holding up. I got a guy on the right holding up. Okay. And you have some distances. Maybe I'll call this R1. Maybe I'll call this R2, and the full length I'll call L. Okay, I don't know if that matches exactly what it said. You guys really did. Okay. Okay. So here, before I go plugging and chugging, maybe ask you guys. I bet you can get this. Because which person, the person on the left or the person on the right, has to support with more force? Has to be stronger. Yeah, the guy on the right. The guy on the right is lifting with more force. If one guy's stronger than the other, then put him on the side where there's more topsoil. Right? So let's do this force diagram. Okay? So I think there's some weight here. I'll call it mg. Okay? And then you guys just told me the force on the right is more than that on the left. So I'll make F sub r a little bit bigger than F sub L. Okay. Now, guys, could you say that these two forces up balance the weight pulling down? Of course, I'm ignoring the applied weight. I know I said that already, but I'm just repeating that, right? Because when you guys did this lab, or isn't this exactly the lab you guys did back on Friday, like the scaffold looking version? In fact, if you can find the scaffold poster in your notes, this would be the answer. Right? So I know two things. I know the sum of force goes to zero, wait, two conditions. Zero. Therefore, these two upward forces balance with this downward force. Okay? And you only know one of those forces so far. You only know the weight of the stack of topsoil. Okay? And the other condition is sum of torque goes to zero, and this is Newton meters. Right? Now this one we're going to set up an equation with. So I need to pick a pivot point. I'm going to choose this point right here. Here's why this is a good choice. See, I just put a gold star right here. Here's why this is a good choice. Because one of my unknown forces acts at that point. Therefore, how much torque does it cause at that point? Zero. It's like if you press on the door hinges of a door, it will never turn the door. So I'm taking two unknowns and I'm going to set up an equation that only has one unknown in it. Ooh. This stack of topsoil, is this causing a clockwise or counterclockwise rotation relative to the left point? Yeah, clockwise. I see he's trying to turn clockwise. But this guy's friend over here on the right side is holding everything back in check, counterclockwise. So got this torque versus the torque. Okay. And since these torques zero out, can I say that the weight of the topsoil times this R1? Here, let me do that. So I know torque is R cross F. Let me put it all together. So R1 times the weight of the stack of topsoils, right? And then, well, I'll go ahead and say minus, right? This full distance L times F sub R. See if you guys are following. This is all equal to what? Zero. Yeah. Newton meters. Right. And you know this, check. You can figure out the way the stack of topsoil pretty fast, check. And you know the full length of the board, check. So you can solve for the force on the right side. Right? Now, after you have that, how do you figure out the guy on the left side? Well, there's two ways to do it. One way is you could set up a new torque equation. You could just change the definition of the pivot point to anywhere else. You know, maybe over on the right side if you want. And you could solve a new torque equation and solve for the force on the left. Another way you could do it is, hey, what about this condition here? You guys remember the forces sum to zero? And you know the way of the topsoil, and you just found the force on the right side. So can you figure out the force on the left side to balance that out to zero? You do that way too. In fact, if you do it both ways, then you can check your work because they should both give you the same answer, right? Right. And last one, and I'll give you guys some pointers on. Number 7, you guys see this wrench trying to turn this lug nut? They say how much torque. Now, I told you guys torque is R cross F. Let me expand this out. Torque. Well, that's R cross F, right? Which is something to do with like RF sine theta. Right. Now, here's where you got to be careful because there's a little bit curveball aspect to this one. You guys see that angle theta is 30 degrees right there? Should I do the length of the wrench, 25 centimeters, times the force times sine of 30 degrees or cosine of 30 degrees? Cosine. Yeah. I know the textbook definition has a sine in it, but it's not sine of the angle to the perpendicular. It's sine of the angle between the two vectors, the length, the radius vector and the force vector, which is not 30 degrees. Because if you really wanted to stick to the textbook and use sine instead of cosine, you don't say 30 degrees. You play off how many degrees is this right here? 60 degrees. That's the complementary angle. So you can either do R F cosine 30 degrees or R F sine 60 degrees, which are the same thing. They're both the same thing. They're both equal to torque. Okay. Because you're looking for the perpendicular components. Right? Torque is a cross product between R and F. Right? All right. So that's the questions that are coming up. Right. Yeah, we got some class time. Go ahead and close this recording right here.